Hello and welcome to the third ASABE Member Hour in our series exploring transforming food and agriculture to circular systems. My name is Chuck Roth and I'll be representing ASABE as your host today. In a minute or so, we'll get started, but first a little housekeeping. Please keep your audio on mute for the entirety of the presentation so we can respect Joe's time. If you have questions, please place them in the chat and we'll discuss those during the moderated question and answer segment at the end. This meeting will be recorded and available for later viewing on YouTube, and Jasper will send out the link after the meeting. Our speaker today is Dr. Joe Segas. Dr. Segas is an assistant professor at North Carolina State University, and he's the principal investigator at the Biocarbon Utilization and Sequestration Lab. He has experience in the research, development, and demonstration of innovative bioprocessing technologies at corporations, universities, and national labs. During graduate school, he conducted independent research as a technology to market scholar at the Department of Energy's Advanced Research Projects Agency, and as an Office of Science Graduate Student Research Fellow at the National Renewable Energy Laboratory. The BUS Lab takes an integrated approach to innovating technologies that utilize and sequester biogenic carbon. The lab's aim is to leverage the bioeconomy for carbon drawdown by bridging fundamental advances in synthetic biology and chemical catalysts with bioprocess engineering to innovate carbon negative bioproducts that range from feed, chemicals, fuels, and materials. Today, Dr. Segas will be leading a conversation entitled Coupling Circularity with Carbon Negativity. Joe?
Yes, thank you, Chuck. So why don't I go ahead and jump right into it and get my screen pulled up. Just 1 second. Does that look okay? All right. Well, good afternoon and good morning to some of you, depending on where you are. My name is Joe Segas. I'm an assistant professor in biological and agricultural engineering at NC State. Chuck, thank you for that very nice introduction. I'm super excited to be here and excited about this emerging concept that I'm going to propose and present to you today, titled Coupling Circularity with Negativity in Food and Agriculture Systems. So the common theme of the series of lectures hosted by ASABE is transitioning from linearity to circularity, right? Or linear systems to circular systems in the context of food and agriculture, right? And so what are linear systems? You know, there's a lot of different definitions out there for both linear and circular systems. I think it really varies on the field, what sector in industry or agriculture or energy that you're looking at. But in general, linear systems have a lot of waste, right? They bring in typically natural resources, they convert them to value in some way, and in doing so, there's a lot of waste generated, which is released into the environment and causes issues to ecosystems as well as human health. So if we can try to eliminate waste, reduce inefficiencies, you know, we would enable circularity. And that's, in my opinion, that's how I kind of view this transition that we're trying to achieve. I do want to give a quick shout out to TFACS. This is the initiative that's being developed and managed through ASABE. I am privileged to be one of the members on the TFACS team. It's led by Jim Jones at UF, and I think we're just getting started, but I'm really excited about the work that we're doing, and I hope you all will chime in and help us out throughout the coming years. So I want to take a figure actually from one of Jim Jones' recent papers, led by author Basso and published in 2021, which was looking at transitioning grain production systems from linear to circular systems, right? And without going too much into the weeds here, you know, when you look at a circular system, you can see, for instance, a linear system, I should say, inputs are applied uniformly regardless of yield potential or spatial variability, right? That leads to a lot of inefficiencies. A lot of the energy that's brought in comes from fossil carbon resources, right? So when you try to circularize this particular system, you bring in new technologies such as electrified on-demand delivery of nitrogen, right? Which can be spatially optimized. So you're only adding the nitrogen where you need it, right? And this is through precision ag and also new technologies that are enabled by plasma and other technologies to bring forth these innovative fertilizer application technologies. You can produce energy on site through biodigesters that utilize agricultural residues and animal waste, right? And so I'm not going to harp on this too much because I think, you know, throughout other presentations, there's been a lot of this type of content presented and explained. So I just wanted to start off with some of the leading work being done by folks in ASABE on transitioning from linear to circular agriculture systems. So this is a figure that my group recently developed. When we think of food and agriculture systems, this is sort of how we envision it in our mind, where we have upstream, which we're just sort of calling traditional agriculture, right? So this is what's done out in the field. Then the agricultural products are processed and consumed, resulting in what we are terming downstream food waste management. And so from these three different parts of the linear system, you're generating waste throughout, right? Whether it's gaseous waste, mostly going into the atmosphere, or solid and liquid waste, which could run off into downstream rivers and waterways or into landfills. That's still considered a form of waste. And so if we try to take this system and enable circularity, it might look something like this, where you have these different quote unquote waste streams being recycled and reused in some way, right? So we're taking these three different parts of the linear system and trying to reuse the outputs, or I should really say cascade the outputs and use them as inputs in another part of the system. Now, in my work, I'm focused on carbon sequestration, reducing CO2 from the atmosphere for more or less permanent sequestration. That's a big emphasis in my research program. And so I've been thinking about this concept of circularity for a while now, and a lot of components of carbon sequestration are usually included, but I don't really view carbon sequestration as circular necessarily, right? Because you're not, at the end of the carbon's life cycle, you're not actually recycling it, you're permanently sequestering it. So it got me thinking, how can we couple, you know, these carbon negative, carbon sequestration technologies and systems coming online to this concept of circularity? And so starting from linear to circular to coupled circular with negativity, this is what we have devised. This is how I'm envisioning it, where you still have all of these recycling loops where byproducts and wastes are eliminated and reused and valorized to create economic value and, of course, bring benefits to the environment. But you're also helping to solve the giant problem of climate change through carbon sequestration. And so this is where these two, primarily upstream and downstream, we think there are near-term opportunities to incorporate carbon sequestration. And that's what's going to be the main focus of my talk today. I'm going to stay pretty broad, keep things pretty high level. I just want to introduce some of these opportunities that have been developed for enabling circularity, but we think could be further developed to incorporate carbon negativity. All right, so just to summarize, right, we have a linear system that's being transformed to a circular system, and then we're bringing in carbon negativity to couple circularity with negativity. So when you look at the principles of achieving circularity, or I should say maybe the requirements of achieving circularity as defined by ASABE and others, right? You need to design out waste, keep products and materials in use, regenerate natural systems, provide economic benefits, and ensure resilience in harmony with Earth's ecosystems. And so my group, we thought about each of these requirements and we thought, how do we couple circularity to each one of these? So for designing out waste, we say, well, why don't we redirect carbon waste to sequestration? And for keeping materials in use, retain carbon in products for the long term, so that keeping material in use will be enabling a circular system, but will also be enabling carbon sequestration if that particular material on its life cycle has a net negative carbon footprint. Regenerating natural systems, if you bring that into the lens of negativity, that could be viewed as restoring atmospheric carbon to pre-industrial levels, providing economic benefits. There's depending on which country you look at, there are emerging markets for carbon sequestration, and then ensuring resilience and harmony with Earth's ecosystems, really just reducing the risks of ecosystem destabilization from climate change. All right, so now I'm going to spend a few slides explaining this field of carbon negativity or enabling carbon negative systems and why that's so important. So going back to climate science 101, just so we're all on the same page, right? The planet receives a lot of solar radiation every single day. A significant fraction of that is reflected back to space. Some of it is retained due to our greenhouse gases, most notably carbon dioxide. For about 10,000 years, the CO2 level was at 250 parts per million. It gave us a nice stable climate, stable sea levels, society developed. We then discovered, in the beginning, we discovered peat and coal in Great Britain. And then from there, fossil fuels were enabled. And we started transitioning fossil carbon from the geological reservoirs to the atmosphere, which started to slowly increase this concentration in CO2, which then reduced the amount of solar radiation reflected back out into space and ultimately increasing Earth's temperature. So we have a CO2 problem. There's too much in the atmosphere. We need to start extracting it and sequestering it, unfortunately. And this, I'm not the only one obviously advocating for this area of research. The Intergovernmental Panel on Climate Change has said that to reach net zero greenhouse gas emissions by 2090, which is required to stay below 2 degrees C warming, we need significant deployment of what are called net negative greenhouse gas emissions or carbon removal technologies, right? So this plot here has global CO2, greenhouse gas emissions quantified as CO2 equivalents on the y-axis with time, right? So just to sort of summarize what we're looking at here, and the IPCC thinks we need to follow this red track if we want to stay below 2 degrees C warming. How are we going to do that? Well, mostly we're going to do it through things like nuclear, wind, and solar, and batteries, right? That's going to get us 70% of the way there, if not more. Unfortunately, we have these other greenhouse gases like nitrous oxide and methane that are really difficult to eliminate. We have some fossil CO2, which we think will be continued to be released throughout the end of the century. So to account for these other greenhouse gases and fossil CO2, we need net negative technologies to the tune of about 10 billion tons per year by 2060. So these other greenhouse gases, right? I think most of the folks in this call are probably pretty familiar with these other greenhouse gases like methane and nitrous oxide. They are not very abundant, but they have a very strong global warming potential, right? 2 tons of methane has the same global warming potential as 50 tons of CO2. And so we're trying to develop technologies to eliminate the release of these. But if we're unsuccessful in completely eliminating these emissions, which seems likely to be the case, I'm sure we can make great progress, but there will still be some emissions. A way to counteract that is to just extract CO2 directly from the atmosphere. So just one more plot here from the IPCC. There's a lot of trajectories out there. well, four in this slide here, LED, S1, S2, and S5. These are four emission trajectories that the IPCC would like us to try and follow. LED doesn't seem very possible. That means we go very fast in emissions reductions. More likely something in S2 or S5. And you can see them probably better up here. S5 is this one where basically we don't start reducing emissions as a global society intensely until 2035. That's more or less what we're on track to do right now. We're not making significant progress. So if we wait till 2035 to really begin reducing emissions, we have to go below zero so that every year, starting in 2050, we're actually extracting, on a net balance, we're extracting CO2 from the atmosphere such that we get down to about 20 billion tons extracted per year. If we want to stay below 1.5, I should mention, this is looking at 1.5, so a bit more stringent. Okay, so we need to remove CO2 from the atmosphere, enable carbon negative technologies. How are we going to do this? Well, when you look at biology enabled processes, there's really two buckets of technologies being developed, those that are natural and then engineered. And I'm going to define them more clearly in just a moment, but I do want to take a second to talk about all the different terms that are thrown around in this field, because it's important to delineate them. So you have CO2 avoidance, which is not equal to CO2 neutrality, which is not equal to CO2 removal. Avoidance is basically carbon-free technologies like nuclear, wind, and solar that produce lower emissions than a reference system. So they're avoiding the emissions of CO2, but they're not physically removing CO2. You have neutral technologies that are things like biofuels, which have the potential to be neutral. As you can see right here, the carbon is taken up during biomass growth. That carbon is then released when the fuel is combusted, assuming all other emissions are nulled out throughout the process. You could have a truly neutral technology. And then you have removal or sequestration or carbon negative systems that actually physically remove CO2 from the atmosphere, and over the life cycle of a particular product, you have net negative. So an example of that would be if you took biomass, combusted it in a power plant, captured all of those emissions, and then put them deep underground, over the life cycle, you would have a carbon negative technology. So four terms here that are mostly interchangeable: carbon dioxide removal, carbon negative systems, negative emissions, and carbon sequestration. So back to this, the two buckets of technologies being developed, we've engineered and natural. Engineered typically involve industrial operations with a lot of energy, exogenous energy, and synthesis reactions, and typically have high rates of CO2 sequestration. Whereas natural typically don't have as much exogenous energy supply or synthesis reactions. They're not really done with industrial operations. They're more managed ecosystems, and they're relatively passive. So the rate of CO2 sequestration per unit area is relatively slow. So this is a figure showing some of the technologies under development right now. In the green, on the green background, these are technologies that are being developed basically on terrestrial ground, above ground, whereas these systems are being developed out in the ocean. And then you have further categorization shown here, where photosynthesis or biology is required for the ones in gray, whereas the dark gray or black is purely inorganic enabled carbon negative technologies. So this is a great slide. I actually think I prefer this table here because I can split down the technologies between natural and engineered. So quickly running through some of these, we have afforestation and reforestation, which would be considered a natural technology, improved forest management, biochar, which I view as engineered, and I'm going to be speaking about biochar in more detail soon. Bioenergy with carbon capture and storage, building materials. This is a pretty exciting space right now. Carbon mineralization as well, pretty exciting space, which has application in agriculture that most people wouldn't really assume. Direct air capture. I'm not going to spend time talking about this. This is purely inorganic. Ocean alkalinity, basically taking limestone and just throwing it in the ocean actually sequesters carbon. Soil carbon sequestration, this is a very hot topic and one that is growing rapidly, although there are some pretty big gaps in knowledge that need to be filled in this space, but certainly great potential. Coastal blue carbon, mangroves, wetlands, and then marine biomass, things like macroalgae, seaweed, iron fertilization, and open ocean, things like that. So if you're interested in learning about these in more depth, I would recommend Googling CDR primer, carbon dioxide removal primer. It's a free textbook online, really great format. I know some of the authors who wrote some of the big chapters and just really well written. So take a look if you're interested. And it's not a very long textbook. It's like 40 pages. Okay, a very important metric with carbon sequestration is the duration of storage, right? How permanent is the carbon once you sequester it? And that's where some of these natural technologies have some barriers to overcome, because the permanence or the security of the carbon is not that great. So with soil carbon, forest management, afforestation, coastal carbon, the duration it spans a wide range, but typically most experts say between 1 and 100 years. Forest fires, for instance, a lot of carbon credits that were purchased for afforestation out west in the US literally went up in smoke, and so all that carbon was lost. Wood products as well typically don't have a very long carbon storage. But I should mention, even if you have a product or technology that sequesters carbon for 70 years, that's still going to buy us time with the issue of climate change. You have other products that sequester carbon for longer periods of time. Chemicals, plastics can go up to 1,000 years, as with biochar. Geological storage of CO2 and subsurface mineralization is largely viewed as the most stable form of storage. You have building materials like concrete, enhanced weathering, which is just like mineralization, and then ocean alkalinity. All of these have pretty long, 1,000+ year periods of time that this carbon will be sequestered securely. All right, so biology, right? This is what I'm particularly interested in. Biomass is great at sequestering CO2. It does it every day through the Calvin cycle, right? Photosynthesis. This is an autotrophic pathway where CO2 and sunlight ultimately produce higher order biomolecules like glucose and cellulose and lignin and hemicellulose to store that carbon. You have other pathways that are primarily based in microbes, like the chemolitho autotrophic pathway, the wood-jung-deal pathway, where CO2 can be taken up with hydrogen instead of sunlight, to also form higher order and higher complexity biomolecules. So okay, we know that biomass is grown every day, well, at least in certain seasons of the year, right? So biomass is already so good at sequestering carbon. Why can't we just rely on what's already out there in native systems? And I think this is obvious to most, but I do want to point out that per year, the CO2 concentration in the atmosphere is not constant, right? Over time, it's increasing due to the transfer of fossil carbon to the atmosphere. But every year we have this up and down, right? So if you look at a particular year, the cycle of CO2 is starting in spring and going through late fall, the CO2 concentration in the atmosphere decreases. And that's because in the northern hemisphere, we have more terrestrial biomass, right? So all that biomass is growing, it's sucking CO2 out of the air. But then during winter, from late fall all the way through early spring, the CO2 concentration increases again, because most of that carbon that was uptaken during fall or during spring and summer is degraded microbially or oxidatively back into the atmosphere. Right, so we have a lot of biomass resources out there today that sequester carbon. It's just that the majority of that carbon is released back to the atmosphere. So, we need to develop technologies to A, valorize it, create value from this biocarbon, and then B, sequester it so it's not released back into the environment. So coming back to this concept of coupling circularity with carbon negativity, I'm going to spend some time talking about near-term opportunities in the upstream bucket and the downstream bucket. So looking at upstream, right? This is looking at on the field we think through precision and regenerative agriculture practices and technologies, there's some exciting opportunities for carbon sequestration. And of course, these are vitally important to achieve circularity. And I think that message has been provided sufficiently in other lectures within this series. So I'm not going to spend a lot of time on how these different technologies upstream and downstream can enable circularity. I'm going to focus more on how they can enable, or I should say, couple negativity with circularity. So we focused on microbiomes, biochar application to soil, and robotics with analytics. So when we look at microbiomes, we're really thinking about soil carbon sequestration, right? And I like to define soil carbon sequestration as making changes to land management practices that increase the carbon content of soil, resulting in a net removal of CO2 from the atmosphere. So when you look at the carbon flux in a particular soil, it's pretty complex. You can break it down by biotic and abiotic carbon flux. So when you look at the biotic, you have mainly bacteria and fungi doing a lot of the either long-term carbon sequestration or short-term carbon release back into the atmosphere. Right. Of course, you have plant matter that is produced through photosynthesis, but then it's really up to the bacteria and fungi to determine what happens to that plant matter during the winter months when the biomass dies. Does it move down and become entrapped and sequestered, or does it oxidize back into CO2 and go back into the atmosphere? And then you have abiotic, which is a lot of mineralization, how the carbon in its various, how the CO2 in its various forms, whether that be carbonic acid, bicarbonate, or mineral carbonates, how it switches back and forth depending on primarily the pH of a particular soil. So when we're looking at microbiomes, research has shown that if you can increase the ratio of fungi to bacteria, you will start to sequester CO2 relative to the baseline of whatever particular soil, whatever particular carbon flux was present in the soil before some type of control that was introduced to try and boost the amount of fungi relative to bacteria. And so bioinoculants are being developed, right? These biofertilizers that are rich in microbes that can be introduced directly to the soil, or interestingly, they can be wrapped into the seed of a crop such that as the crop begins to grow, these microbes live within the roots and help to adjust the microbiome to sequester carbon. Another pretty easy approach to manipulating the carbon flux in soil is altering the pH. That can actually sequester carbon all by itself by managing how you add ag lime to soil can induce carbon sequestration. And then very importantly, regenerative practices like no-till and cover cropping will certainly begin to sequester carbon in your soil because you'll be introducing much less oxygen throughout a year, and therefore reducing the amount of aerobic respiration that can take place and keeping things more anaerobic and allowing the carbon to begin to build up in the soil. The next one is biochar, applications of biochar to soils, right? And so on the left here, this is a field study being done by my colleague Alex Woodley here at NC State. He's in soil science. In Eastern North Carolina, we have a lot of sandy loam soils, which are not very amenable to soil organic carbon accrual. Like the organic carbon does not accumulate very well in these sandy soils. And so no-till and cover cropping certainly help, but they don't help as much as they do in the Midwest. And so they're looking at taking this exogenous form of carbon, which is biochar, and adding it to the soil. And so what you can see here on the right is in a typical soil, there is a maximum, a plateau with increasing the organic carbon content. And so if you want to increase the total carbon content further, a great application is biochar. And that's what's being done in the soils, as I mentioned, now in Eastern North Carolina. By doing this, not only are you bringing in physical carbon, more carbon into the soil, there are some indirect effects of adding biochar to soil that help with carbon sequestration. So adding biochar has a negative priming effect, which basically means that the rate of decomposition and degradation of carbon in the soil microbially is decreased when you add biochar. In addition, depending on how it's added and managed, you can certainly add too much biochar, but if it's done correctly, you can actually increase the soil fertility and crop growth. The next one is looking at robotics and analytics. Right, this is a rapidly growing sector of our field. Precision ag, of course, I think most people on this call are probably familiar with it. And up until this point, most of the applications have been looking at nutrient management. I'm not really an expert in this field, but that's the impression I'm getting. And through the literature review my group and I have been doing, that seems to be the primary focal point. But what's interesting is a lot of these technologies being developed can be used for measuring and analyzing the carbon content in soils on large spatial and temporal domains, right? And that's going to be a big deal as farmers begin to incorporate these practices to sequester carbon. If they want to earn credits, they need to prove to whether it's the government or the market managers that they are truly sequestering carbon. So there's a study shown recently that if you take simple near infrared visual spectroscopy, you can get really good correlation with actual or organic carbon content in soil, as you can see right here. And so if you can just take this technology, modularize it, put it in a robot, you could theoretically go out and autonomously measure the carbon content in your soil, which I think is really exciting. And it's being done. I should mention, it's not like this isn't brand new. There are definitely groups out there trying to incorporate or couple precision ag technologies with carbon sequestration. That is definitely being done. But there's room for growth. I should just sort of conclude on that point. All right, so that was a brief high-level overview of some opportunities we're excited about in more of the upstream precision ag and regenerative ag applications within food and agriculture systems. Now looking downstream, right? What do you do with all of this waste material that's generated, right? So biorefining, this is a broad field that has been under development for decades now. And we're starting to realize that in the future, perhaps biorefining will not be valued so much for its energy production or its material production or chemical production, but more so on its ability to sequester carbon, right? There might be a future where that's the reality. And so we've identified 4 general biorefining technologies that we think have near-term opportunities for carbon sequestration. So to zoom out, right, again, biorefining is a broad field. There's a lot of different biorefining platforms, conversion processes, and primary bioproducts and secondary bioproducts that are commercially mature or are still under development. We're going to be focusing on these 4 because when you view these through the lens of carbon sequestration, particularly in the near term, these are the ones that excite myself and my colleagues. So let's look at fermentation and specifically ethanol fermentation, because that is a very mature industry in the United States, as well as other countries, most notably Brazil. This is the life cycle of basically ethanol biofuel production, right? So you're growing your primarily corn in the US. That is a carbon sink. You have all these different operations that act as carbon sources back into the atmosphere, transportation, pre-processing, more transportation. You then have the fermentation, the process or the refining of the biocarbon into ethanol, right? So you're taking primarily glucose and you're making ethanol and CO2. And so off the top of these fermenters, these 100,000 gallon fermenters, you have nearly pure streams of CO2 just being vented to the atmosphere. Right, so that's some very low-hanging fruit to the tune of 50 million tons of CO2 per year in the US that we could capture and sequester. Right, just finishing up this life cycle, the fuel is then transported to distribution stations where it's then put into our vehicles at roughly 10% of every gallon. That is then combusted and the CO2 is released back into the environment. Right, so between soil carbon sequestration and then geological sequestration, there is the opportunity to convert this entire life cycle to carbon negative. And this is reality. ADM, Archer Daniel Midlands, is sequestering over 1 million tons of CO2 today. Well, I should say, sorry, per year on an annual basis, but it is happening at their Decatur mill in Illinois, shown right here. And this is where the CO2 is first compressed into a liquid and then injected, I believe, over a mile underground or around a mile underground into these saline geological reservoirs where the CO2 can be stored. Next, we're going to look at anaerobic digestion, right? This is a lot of folks in our field are very familiar with this technology. Similar to fermentation, you're generating CO2, right? In this case, you're not making ethanol, you're making methane plus CO2 from various organic waste materials. Methane has been the primary product of interest because you can use it for energy. However, when you upgrade the biogas, you're separating out CO2, and again, you're generating this very pure stream of CO2, which could be captured and sequestered or utilized in some way, right? So, the ADM, they're taking their CO2 from the fermentation process and they're injecting it deep underground for permanent sequestration. You could take that CO2 and use some sort of innovative bioprocess to convert it into a bioplastic or some other product that creates value and sequesters carbon. And then in this process, you also have these digestate solids, which contain some carbon and could be applied to the field for soil carbon sequestration. So this is from a paper by Lee et al., and it's just looking at a few different configurations of anaerobic digestion. This is a simple sort of baseline case where the biogas is combusted without any type of upgrading, and the CO2 is just vented. You can upgrade the biogas, right, which I just showed generates a pretty pure stream of CO2, which is exciting. You can bolt on CO2 capture to basically system A up here. That's what system C is. This is pretty costly to do. Economics look better if you upgrade it to separate the CO2 instead of combusting and then separating the CO2. But this is certainly a pathway that could be investigated. And then you have this one down here, part D, which is actually oxy-fuel combustion, where you take the biogas and instead of using air as the oxidant, you use pure oxygen, which gives you a stream of basically CO2 and water. And the water can be condensed out pretty cheaply, and then you have pure CO2. Lastly, there is some research looking at taking the CO2 from your digester and recirculating it back into the digester, which is shown to sequester carbon and increase the methane yields and basically result in less CO2 emissions per standard meter cubed of methane produced. The next one is pyrolysis, which is a very important technology. It's basically a thermochemical technology that treats biomass under oxygen limiting environments, very little to no oxygen present. And when you do this at relatively high temperatures, between 400 and 800 degrees Celsius, you get three products. You get a gaseous product, a liquid product, and a solid product. I already spoke about biochar, right? So there's a lot of interesting opportunities to amend soils with biochar. You can use biochar in different products. The gas can be combusted directly to produce energy, and that CO2 perhaps could be sequestered. But there's a growing application that I feel like a lot of people aren't super familiar with, which is very intriguing to me, and that is taking the liquid, the bio oil, and pumping it, basically pumping it back where crude oil came from in the first place. And so there's a company called Charm, which is doing just this. They're taking their bio crude from pyrolysis, which is a thick bio oil, and they are just pumping it deep underground to get carbon credits. And so it's basically for 150 years, we took oil out of the ground, and you can take biomass, convert that biomass back into oil, and put the oil back from where the original oil came from, right? That's sort of the high level vision of this company, which I think is very intriguing. And they have done studies to see how this reacts in the subsurface. And their data so far shows that it basically just solidifies and becomes a very hard form of carbon in tiny pores deep underground, which ultimately sequesters the carbon. Lastly, we have gasification. I'm showing this slide because really when you look at hydrogen generation technologies using biomass as the feedstock, nearly all of them have opportunities for relatively low cost CO2 capture and sequestration. And that's because when you're stripping out the hydrogen from biomass, you're going to end up with a lot of CO2. And so typically, depending on your separation technology, you can separate the CO2 relatively cheaply, at least compared to the effluent from like a biomass combustion plant where it's diluted heavily in nitrogen. Typically, these different biohydrogen technologies have pretty high purity CO2. And so gasification is intriguing because it's of these different technologies, it has a pretty high technology readiness level. And again, we're trying to focus on near term opportunities. And gasification is not new. It's been tried at scale. It's failed brilliantly at scale, but there's been a lot of progress specifically with using municipal solid waste in the US and in the EU. And I do want to give a little plug to this company called Moat Hydrogen out in California. They're a startup that I'm on the board of. They're doing some pretty exciting work in California on using biomass feedstocks for gasification, where they're actually targeting CO2 as the main product. Hydrogen is a byproduct. And they're using the low carbon fuel standard in California as their means of profit. All right, lastly, with biorefining, I want to introduce this concept of bioproduct cascading. This is a common concept used in the wood product industry. And I think it could be applied more broadly to all the different bioproducts, not just wood products. And the idea here, and you know, I think when you're trying to learn up about circular systems, you know, it's pretty ambiguous, you know, how the term circular is defined. But I think in the context of biorefining, you can really think of cascading. This is how I view a circular system in biorefining. It's basically trying to take advantage of every byproduct and eliminating waste to the best degree that you possibly can. And I like this plot because it shows what happens to the value of these different products as they move on, right? So once you reach basically very little value, at that point, you don't have much opportunity. It needs to be landfilled and maintained appropriately. But until you get to this point, you really should not be landfilling or volatilizing into the atmosphere any of these different byproduct, co-product streams in these biorefining technologies. All right, so to conclude, I want to talk about life cycle assessment briefly. I think in our field of ag and bioengineering, this is a tool that's becoming more and more important. It's been important for a while, of course, but as companies are trying to reduce their carbon footprints and their overall footprint on the environment, they need to quantify these different sources of pollution and waste in their systems, and that can be done through life cycle assessment. So when you're looking at carbon, the question is, does a particular food and agriculture system successfully remove more CO2 from the atmosphere than it emits? All right, that's what we're looking at when we're trying to sequester carbon. And so coming back to the ethanol fermentation process, right, I had shown these different sinks and sources of carbon, right? This is just a high-level overview of how you should think, systems-level thinking to enable carbon sequestration. And so you can quantify all these different sources and sinks on a common unit. So in this case, we're looking at kilograms of CO2 equivalent per ton of ethanol produced. You quantify that for all of your different operations, right? Again, this is a super simplified. This is what I show my undergraduates just to kind of get them excited about this concept of life cycle assessment. And then you can just tabularize it and sum up the CO2 removed and subtract it from the amount emitted, and you should be greater than zero if you have a truly carbon negative food and agriculture system. All right, so who's taking this seriously on the corporate side? A lot of companies, just to point out a couple, Apple, they're looking primarily at natural technologies, so afforestation, reforestation, soil carbon, that's what they're interested in. Microsoft is more interested in engineered solutions, surprisingly. And Microsoft has made a very bold claim. They have committed, whatever that means, committed to removing all of their removing all of their historical emissions. So dating back to the 70s when they were founded, every molecule of CO2 released directly and indirectly from their operations, they will remove from the atmosphere to ultimately reach a net zero company through the lifetime of their existence, which I think is really neat. And it's a concept that a lot of folks are starting to think about. It are these historical molecules of CO2, right? CO2 is very inert. It lives in the atmosphere for a very long time, at least a certain fraction of it, right? So CO2 that was emitted when, my grandparents were first learned how to drive, like that's still in the atmosphere theoretically. And so you can have these sort of creative concepts of historical emissions and removing those emissions from the atmosphere. Sorry, I keep thinking I'm almost done. So the US policies, that's right. There are some opportunities here, right? This doesn't really make much sense unless you can monetize it. And so typically that comes in the form of policy regulation. So in the US, we have the 45Q, which is a tax credit managed by the IRS that will give companies up to $50 per ton CO2 utilized and sequestered. In California, you have the low carbon fuel standard. They just recently allowed CO2 sequestration as a viable pathway. And the cost in that market is much higher, greater than $100 per ton. There's some talk about what's going to happen to the renewable fuel standard. It's being renewed in 2022. And there's whispers that carbon sequestration could be a major component of the fuel standard moving forward. Let's see. That's to be determined. And so I just want to conclude with, I think in this field of carbon negativity and circularity, for sure, we need carbon scientists and engineers from all sorts of different disciplines. I think ag and bioengineers can be leaders, but we definitely want to make sure we include others, particularly those from the social sciences, because as we mitigate climate change, there's been a lot of work shown that the deployment of new technologies and new infrastructure to mitigate climate change is going to be disruptive to society. And we need to make sure that marginalized communities, low-income communities are not further marginalized and they are not left out, right? So that's something I like to always try and end with. So with that, I want to thank you for your time, and I'd be happy to answer any questions if we have time. Oh, I'm sorry. I want to say thank you to my lab group. Sorry about that. Yes, these are my grad students. Really, really great. Trevor Vuk, Julia Kenneth, Lillian Lower, Vanessa Rondon, and Ethan Woods. So big thanks to them for helping me.
All right, thanks, Dr. Segas. We've got a few comments and some questions in the chat. So I'll just, you guys can read the comments as we go here, but I'll read the questions off to you and then you can respond. So I think the first question we had was, you had an anaerobic digestion chart. CO2 concentration was more than 95%. Is that a unique scenario? I'm not sure what slide that was on.
Yeah, that's not always the case. I should have clarified that. It depends on your upgrading technology. How are you upgrading your biogas? The biogas coming out of the digester is only about 50% CO2. But once it's upgraded, you're separating the methane from the CO2 and the hydrogen sulfide, and maybe some other sulfur-containing species that might be present.
Thank you. Next question, are there any markets where biogenic CO2 capture is treated differently from fossil fuel originated CO2?
Yeah, That's a great question. And so the 45Q, which is the largest opportunity in the US right now, does not, well, they've been revising this so often. The latest revision that I was sort of caught up to speed with was about a year ago, and biogenic was not differentiated from fossil, but I think we're moving towards that. Yeah, we're moving towards a premium placed on biogenic carbon or direct atmospheric carbon over fossil carbon for sure.
Thank you. Next question, you presented a lot of great options. Most of them likely have both co-benefits and disbenefits. Do you have a sense of where the field is in terms of balancing that success in carbon sequestration versus potential other benefits? So how do you balance those? Specifically mentioned pollution, labor, health effects, etc.
Yeah, yep. So that's another a problem that has to be carefully addressed. Is any disruptive technology, well, that has a lot of benefit and can help solve a couple big problems, most likely if it's deployed at massive scale, will have some unintended consequences. And so you try your best to avoid those, and that's why life cycle assessment is key to looking at not, I'm particularly interested in global warming impacts, carbon footprints, but there's a lot of other impacts, including social impacts, that you can quantify through LCA. And so you just try to do your best job of looking at the whole system and quantifying all the impacts. But it's a major challenge. There's a lot of uncertainty in these LCA models. But that's why we have experts that develop Monte Carlo simulations and make sure that the uncertainty is accounted for.
Thank you. Another question, since water vapor is also a greenhouse gas, what is its global warming potential compared to CO2?
Yes, so that I am not sure. Water vapor can be, yes, it can be a greenhouse gas, but I think that particular contribution to climate change is fairly complex because there's also an emerging concept of doing what's called marine cloud brightening, I believe, where ocean water is sprayed up into the atmosphere to make tiny droplets, to make clouds, to actually reflect sunlight. So it's got some albedo plus greenhouse effect. So that's really a question for a climate scientist. So I can't really answer that one.
Understood. There's a couple more questions. I think we kind of need to wrap it up here to respect folks' time, but I'll relay those to you, Joe, and then maybe we can cover those offline as well. And I'm sure Joe wouldn't have a problem with folks reaching out to him directly if you have more questions or want to learn more about him and his work. So with that, just wanted to say thank you to everyone, to Joe, and to everybody else who was on the call today and participated. Also, especially ASABE Director of Membership, Jasper Cunningham. I always want to thank him. It's helpful in setting up these member hours. And to some other folks as well, some on this call, some that weren't able to participate, that have helped make this series and member hours a reality. So as previously mentioned, this is the third in a 5-part series on circular systems. So we've got a couple more events planned, and we're also investigating some future events beyond that. So our next installment is in a couple weeks on Thursday, October 28th at 1 p.m. Eastern. Stephanie Herbstreet is going to be discussing renewable natural gas, and more information can be found at the link. I'm going to drop it into the chat here for everyone. So you can go there to get registered for that event in 2 weeks, and we'll continue this series. We've got, like I said, we've got 2 more currently planned, and we're looking to add a few more here as we round out the end of the year. So look forward to that, and you'll be seeing some more communication on that as well. And thanks for your participation today, and thanks, Dr. Segas, for your presentation.
Thank you.